The stage is yours.
Thank you. Thank you very much for the invitation. I was fighting with PowerPoint, but I'm afraid I have to fight again because for some reason it switches, it projects to the second screen, and when I do the software demo, I'll have to reset it again. I'm going to talk about Bayesian networks and learning Bayesian networks from data, which is really good data science. But in order to be able to do that, I have to tell you something about Bayesian networks, because otherwise it's going to be hard to follow. Just out of curiosity, how many of you have worked with Bayesian networks or know what Bayesian networks are? Well, a handful. That's 1/4. So I'm going to spend a few minutes first, maybe 10 minutes on Bayesian networks, and then go to causal discovery and learning them from data. Bayesian networks are essentially acyclic directed graphs that consist of this qualitative structural part and the quantitative part. The structure is essentially blobs, nodes, which represent random variables and connections between them, which I'll come back to that later. Sometimes it's convenient to think about them as causal relations. So two variables are in causal relation. One of the variables at the beginning of the arc is influencing the other one. Is it better now? Then the quantitative part are numbers, which in nodes without predecessors are prior or marginal probability distributions, and nodes with predecessors, with parents, encode conditional probability distributions, conditional on the parent. The numbers can be taken from a variety of sources, like textbooks, literature, expert opinion. They are Bayesian, so probability is not a limiting frequency, but it's a measure of belief. So they can be taken from expert opinion. And also from databases, which is the most important thing from the point of view of this audience. What can we do with them? We can perform Bayesian inference. We can calculate posterior probability of any variable of interest given observations. That's kind of in the theory. But in practice, there are questions like, for this network, which is a very simple network involving a few variables from the domain of cervical cancer, you can ask, what is the probability of, I'm sorry, this is hepatitis. What is the probability of hepatitis in an alcoholic patient with jaundice and ascites? Ascites are small things you can see on your skins. You can ask the question, which disease is the most likely, or which tests should we perform? I'll show you that this kind of queries live. So when we ask this query, essentially what happens is there's a calculation of a posterior probability, conditional, that can be imagined as spreading information from the nodes that have observations to the rest of the network and the things that we are interested in. In this case, the red nodes are the diseases. Bayesian networks are very close to systems of structural equations. And in fact, even Excel spreadsheets are their far distant relative. So here is a system of simultaneous equations which can be also captured as a Bayesian network. Now, the mathematics of it is that, I promise this is just a couple of slides. There is a way of capturing a joint probability distribution over variables. Joint means how these variables are jointly distributed together. You can factorize them, and for every variable behind the conditioning bar, you put an arrow from the variables behind the conditioning bar to the variable before the bar. So here is one possible factorization. Every joint distribution can be factorized like this. Here's another one, which results in a different network. And here's yet another one. And there are, I think, 24 of these for 4 variables, combinatorial number. Some of these factorizations are more interesting because if we know about some independencies in the domain, we can simplify the product. when we simplify the product, we have fewer arcs, and that means fewer numbers. If you want to represent a joint distribution over n variables, you are dealing with, in binary case, 2 to the power of n parameters. That's out of the question for any type of system. But with encoding independencies, we can reduce that number. So this is one way of thinking about Bayesian networks. Lack of an arrow, of an arc, means independence. But it's much better to think about it as causal graphs. And in fact, it's not terribly outrageous to do so. So causal arcs means, for example, obesity is a causal factor in hepatic steatosis. It is a risk factor, in fact, to that. So you can think about the arrows, the arcs, as causal influences. Now, independencies lead to enormous savings. For example, here is a network with 70 variables. They are more than binary, but if they were binary, we would need around 10 to the power of 21 parameters. With the independencies, we can represent this domain with just 2,100 parameters. So the savings are enormous. Here's another network that would need 10 to the power of 13 parameters. In this case, we were not very worried about the numbers because we had a huge data set, almost 1 million cases. So we just learned the parameters, 300,000 parameters. Here's another example of a real Bayesian network used for diagnosis of diesel locomotives. 2,100 variables. That would mean, that would require, I'm just showing a blow-up of a piece of it, it's a spaghetti. It would require 2 to the power of 2,000 parameters. Just for your kind of information reminder, that's around 10 to the power of 600, which is much bigger than 10 to the power of 82, which is the number to be believed to be the number of atoms in the universe. So the savings are just enormous. And the savings make it practical to use probability theory in modeling domains and in reasoning with them. So that was the introduction to Bayesian networks. Here is one of the applications. There is a company in Poland, in Wrocław, which has created a few years ago a branch in the United States where you can go to and perform self-diagnosis. Our software and Bayesian networks are under it, which is quite a challenge because it's a domain of, I think, internal medicine, quite a lot of variables, and still quite practical. What I'm going to do now is I'm going to do a brief demo of the software and talk about learning in the context of the software, which is going to be much easier. Okay, and I need to fix what PowerPoint has. Oh no, we are there. I think very good. So the software is something that we developed in my lab at the university around 22 years ago. And just a couple of years ago, we made it commercial. You know, as every good American professor, I'm very practically minded. So we started the company, and we are now selling this product. Before we started doing this, we got thousands and thousands of users. Practically, academic market belongs to us because the software was free, and it's still free for academic users. So if you work at a university, you can just use it in teaching and research. Okay, so here is the software. Let me show you a Bayesian network. Here is a network that models liver disorders. So here we have the rectangles are diseases, and the other things are just other variables. The blue ones are risk factors. The green nodes are symptoms and test results. What you can do with it is you can start reasoning. For example, observing jaundice results in updating the probabilities of the diseases. It's a diagnostic model. For diagnosis, we have special extensions, so you can invoke them. And what this does is it shows you what you can do with probability, with joint probability distribution. You can do anything. In particular, what we do here is we pull out all the diseases from the model to this window, all the possible observations to this window, things that are observed already right here, and then the possible observations are rank ordered from the most to least informative as far as this disease goes. I can perform differential diagnosis. Let me pick the 4 most likely diseases. Now, here is the best test to distinguish between them. So, differential diagnosis. We are doing it, pursuing it, until there is a clear winner among the things. Here we are. This test has made it. PBC, primary biliary cirrhosis, is the most likely disease. Always probabilities, as you see, because the world is uncertain. We never know for sure. What else could I show you? Let me go over to, just one more thing. The huge model, the locomotive diagnosis. As you see, it's huge. Let me show you the whole model. The same thing we can do. It's obfuscated. The user didn't give us the original model with all the names. You can automatically scramble the names. So the names are scrambled, but we know that these are the problems with the locomotive, quite a number of them, and these are the possible observations. It's even with this laptop, it's well, it takes a fraction of a second. But as you see, calculating with them is really not terribly expensive. Even though updating in Bayesian networks is NP hard, has been proven to be worst case NP hard. Now, the main part of the talk, which is learning. So imagine you have a data set of customers of a bank. Let me make it a little larger so that you can see what's there. The first line is are the names, labels of the variables. Columns are measurements of a variable, and they are simultaneous. Every record, every row is a customer. So it's a flat table. Gini also interfaces with databases, but ultimately when you learn joint distributions, you need a flat table. So when we have that, what we can do is we can learn a new network. There are a number of algorithms for doing this, but let me just do this. Here we are. We have a network learned from data. I don't have enough time to tell you more about the algorithms used, but if you remember, I talked about independencies. Absence of arcs are independencies. There are ways for, of course, independence testing to know where the arcs are missing. There are also ways of orienting the arcs, because there are clear rules when things are independent, when things are dependent. So now let me show you that the network I learned in a fraction of a second from the data can be used in inference. So if I want to know whether my new customer will pay off the loan, this is the credit worthiness variable, I can just start asking questions. What's your age? What's your payment history? Profession, etc. And you see the posterior probability of distribution over this variable changes. So I can embed this now into an expert system quite quickly. One more thing I wanted to show you, this is very close to, in fact, philosophers are working also on this methodologies. It's close to learning causal structures, so causal discovery. Traditionally, to learn causation, the causal directions, what we do is we perform experiments in which we manipulate a variable, independent variable, and see whether the dependent variable has changed. If it has, then there is a causal connection between the two. Now you can do that these days with just data, pure observation and pure analysis. Here is a real data set. The previous one was not real. Here's a real data set describing American universities. There are 170 of these. measured over variables. For some reason, it's not listening to me. Okay. Spending per student, average percent retention. So how many students stay after 1 year in college, in university? Top 10 percentage of students who were in the top 10% of their high school class. Test scores are comparable to entrance exams, probability of accepting an offer from the university, faculty salary, etc. So let me show you the problem. Carnegie Mellon, I was still at Carnegie Mellon at the time, asked us to look at the causes, find out what the causes are of low student retention. So why are students leaving the university? Of course, you might say they are leaving because they cannot handle it, but actually most of the people leaving are leaving for other reasons. And this is a histogram of retention over all US universities. What you can see here is that some universities are losing around 80% of their students in the first year, which is terrible because of the logistics. You need more professors, more rooms, only to find most of your students gone. Carnegie Mellon was at that time around 60-something%, but they were worried because they wanted to be in the ranking, they wanted to be high, and retention was one of the criteria for ranking. The data set is from US News and World Report magazine, which publishes the ranking every year. So they asked us what is causing the low student retention, and again, these methodologies, we didn't have this software, we had other software and algorithms, but here is what you can do. Within, again, a fraction of a second, you analyze the data and you see which things are independent, which things are directly dependent, and for which variables you cannot figure out the direction of dependence. As I start playing with the significance level of individual decisions, I can actually, let me again do the same algorithm. I'm changing just the significance level to 1 in 100. We have the variable of interest, the one that interested them, connected only to one variable in this small set, to the average test scores, which is very closely connected to the top 10, which is another measure of the quality of incoming students. So test scores, a measure of quality of incoming students, and this variable, another one. In this case, the algorithm wasn't able to find the direction of the influence, but actually with some expert knowledge, which you can enter for the algorithm, it's quite clear that retention happens a year later after the students were admitted. So the arrow has to go in this direction. So it goes in this direction. You can create a Bayesian network out of it and start using it again to predict how much the retention will increase. This story actually has a very nice happy end because they listened to us and they performed a real-world experiment testing whether there is indeed causal relation between these variables and retention. They changed the admission policies, offering small stipends, partial funding to students with the highest SAT scores, which are the standardized exams, and they indeed found increased retention within 1 year, which is kind of nice because there are not so many real-world studies. I'm going to rush because I have time. We can always come back to the presentation. So causal discovery, just one slide reminding you that with data you can, with data and structure you can always learn the parameters from the data set. That's fairly easy. That's just counting really. But you can also learn the structure. And there are good, solid, well-grounded in statistics methodologies. They're so solid that even philosophers are, it's not uncontroversial, but they are also believing that they do work. You can, under certain circumstances, discover causation. We learned the representation of joint probability distribution, because it's useful. We can use it directly in expert systems, in kind of decision support. Obtaining causal insight is another one. When you do it interactively, you can play with the data, and you can tell the people, the company, why their customers are leaving. What methodology for advertising works best, right? Etc., etc. A lot of data. We can find out what causes what. A little bit about our company. This is when we were still at the university lab. A lot of enthusiasm. Over time, we had like 20 or 30 people doing different things with one another. Here is the software. It's still a university picture. In 2015, we created a company. So we have a lot of things. We have this API in C++, fully portable. Then we have wrappers for .NET, for Java, for pocket computers, for phones. And then Genie is what you saw, the GUI that you saw interactively. We are tested in Pennsylvania, but we have a development department in Białystok. That's not quite yet our office, but we are working on that. The software, because it's actually very reliable. We participated in speed competitions. Quite possibly, we are the fastest. Quite possibly, we don't know for sure. And also as reliable as any other commercial company. There are several of these. We limited some of the things which were still a little flaky, kind of university quality. So it's a little bit limited, but the important things are there. And we are hiring also. So that's it. I just wanted to reiterate the things that I said throughout the talk. Bayesian networks are practical. So probability theory, which was believed to be impractical, suddenly has become practical. They're actually quite old. They are already 30 years old or so, Bayesian networks. Although a lot of development happened in the last 20 and then 10 years. Learning is exciting. It's a different, powerful way of doing science in terms of causal discovery. We have done a lot of learning work also. It's also one of the strategic directions for the company. And we're looking not only for people to work with us, but also for partners. So if you see any opportunities for collaboration, let's get together. Thank you.
Thank you. So time for questions.
Mic test.
It's working.
I'm curious about your claims to be able to discover causality. In particular, how can you know if there isn't a problem of simply like omitted variable?
Okay, and that's an excellent question, of course, because in general, you cannot discover causation from data. If you just have two variables, there's no way you can detect which causes which, unless you make assumptions. You assume away any latent variable, and you assume that A is in time before B. Then you can say, oh, A causes B, because there's nothing outside. I assume that away, and there's time precedence. In general, it's impossible. I mean, in general, it's not always possible, but there are cases where it is possible. When you have, so correlation does not mean causation, absolutely true, but very misleading, because if you have a pattern of correlations, if you have three variables that show you a certain pattern of correlations, dependencies, you can actually determine that there is a causal relation. If I had 5 minutes, I could show you a few examples of that, but maybe since there's another talk, we can postpone this. Let me point you to the literature. Unless we have time, I can.
Maybe during the after party or something like that.
Yeah.
We have this room probably will be open for after our talks, so you can still use some time and talk up here. If not during the after party. Another question.
Hello. I would like to thank you for the excellent introduction, because I have come across this, but this probably makes more sense more than any other literature that I've read so far. Just trying to understand standard machine learning approaches that, like, for example, a random forest classifier to classify if a customer is going to default or not, is an approach that is also followed. I would like to understand where the probabilistic Bayesian approach fits in, wherein the standard learning approach of using simple classifier, I mean, where would one fit better?
Okay, so first, what are the advantages of this over anything else, right? Well, I would divide things into subsymbolic and symbolic. Subsymbolic neural networks, symbolic random forests, and everything else where you have think explicitly and you have some structure. Bayesian networks tell you, I think, more about the structure. So what things depend on what? What are the connections? This is the first thing. Now, how do they compare? In terms of accuracy of predictions, I cannot guarantee you that Bayesian networks are going to be more accurate. In fact, random forests for any given data set may perform better. But Bayesian networks can also perform better. I'm not saying they are worse. No. It's just that, you know, many methods, you cannot predict a priori which are going to be best. On the average, yes. But so Bayesian networks are just as good as anything else in terms of prediction. The additional thing is giving the structure and of the problem. Now, how do they perform? How do they look like? Random forests will give you a prediction. Decision trees will give you a prediction. This is class A, right? Bayesian networks will not do that for you. They will tell you, here is the probability distribution over classes. Class A, 0.91. Class B, 0.02. Class C, so much. It's you who makes a decision. Typically, you will say, I'm picking the most likely class. But not always. A cancer probability of 0.1 is something that one has to look at. So if you combine probability with utility, and that's another mathematical theory of expected utility theory, decision theory, then you can make decisions also. When you make decisions, you don't want somebody to tell you this is class A, class B. You want to know the probability of that class. Even weather forecasters tell you the probability of rain is 70%. You want to know it. You don't want to hear there may be rain or there's going to be rain, right? So the main difference between Bayesian networks, probabilistic approaches, and the, I would say, logic kind of base, which tell you which class it is that you have this intermediate stage probability distribution, which allows you to make a decision. Does this?
Thank you.
Okay, thank you so much. I think we'll leave the rest of the questions after our talks. So thank you so much, and applause, please.